Welcome, everybody. My name is Nicholas Lane, and it's so great to see so many of you joining us today for our first information session. I have to admit, this is the first time we have done this information session before with the Cambridge AI Academy. And so we're really excited to see how it goes, and we really value your feedback. So feel free at the end of the session, let us know what you think and what you want to see more of done in the future. But we're excited to present the sort of opportunities to connect with you further. I'm going to start sharing my screen, and we can begin our presentation for today. Let's see. So bear with me 1 second. And you'll see on the screen right now that you'll see the title of what we're going to be talking about today. So the focus of this short information session is going to be on what we're calling the deep learning renaissance. And this is actually just a tiny fraction of some of the material that we cover in a current course with the AI Academy called Deep Neural Networks. And this is a course that both Philip and myself teach. Now, before I begin and showing you a bit about the course and giving you a sense of the flavor of the material, I just want to tell you a few things about the AI Academy in general. So let me just advance the slide. And so the Cambridge AI Academy, it's a fairly recent initiative that's been in existence for a couple of years now. It's entirely faculty driven. And so what's happened is that a few of my colleagues across Europe and the UK have decided to start teaching courses designed by ourselves, where we teach it to international students, because we see that there is a real demand out there. We want to have an opportunity to reach as many people as possible. And so we've designed a series of courses that are each tightly related to our core specialities. I'll be telling you more about my colleagues on the next slide, but I just want to give you a flavor of what is available in the Academy. We try to cover a real diverse set of AI courses, including deep neural networks, which is sort of the underpinnings of what we're talking about in this information session, but also machine learning systems, graph neural networks, finance and machine learning, mobile robotics, and mobile health. And we intend to expand these offerings in the future. And as I mentioned before, these are courses designed by people like myself, who are university academics, and we're just producing these courses for remote consumption. And we've deliberately tried to find colleagues who are really truly world-class in what they do, and they all have faculty positions in well-known universities. So myself, I'm at the University of Cambridge, just as Philip is. We have academics from Warwick, Edinburgh, Amsterdam, and Avignon. So let me tell you and introduce each of them. So there's myself. My name is Nicholas Lane. I'm a professor of machine learning systems at the University of Cambridge. There's below me, you see Philip Swoboda. He is also at the University of Cambridge, and we co-teach this deep learning course that is the focus of the information session. And in fact, actually, he and I have taught courses of this kind in Oxford and at Cambridge, and now remotely for the Cambridge AI Academy for many years now. And so we're really tapping into a lot of experience about what it's like to teach people the material we're talking about today. Next to my picture, you'll see Chris Liu. He's an assistant professor at Edinburgh. He specializes in things like robotics and computer vision. Below him is Hong Kai Wen. He's a professor at Warwick. He specializes in areas such as cyber-physical systems, databases and AI. Next to him is Titouan Parclay. He is an associate professor at Avignon. He's a specialist in the areas of speech recognition and graph neural networks. Above him is Cecilia Moscola. She's a professor at University of Cambridge. She has a long history of mobile AI, and she's going to be teaching about mobile AI health. And then finally, to the right of these two images, you will see Tomislav Ladika. He's an associate professor of finance in the University of Amsterdam. And so this is the pool of talent that we've assembled behind the academy. It's a very flat structure. It's just a series of academics producing courses that we're passionate about, and they want to disseminate this information to students like yourself. So I'm really delighted that so many of you come today. It's really interesting. And in future sessions, I think what we might want to try to do is make it more interactive. The way I've prepared this today is simply just to kind of tell you more about the academy, give you a flavor of what some of the content is that we have in the particular course that I'm delivering, along with Philip, and really start to kind of connect with the students. But perhaps I think in future sessions, we can start to be more interactive. So let's move on to the material. So the course that Philip and I teach is about deep neural networks, and we begin at the initial stages of deep learning, allowing anybody without a lot of background in the area to sort of really immediately understand the space and get a feel for where it's come from. And so one of the things we like to talk about is the fact that where did deep learning come from? And what was it like at the origins? Because some people would have heard different notions about how deep learning's been around for a long time. And so we like to explain that there are many different sort of potential points that in history you can point to indicate, oh, this was the origin of deep learning. This is when it started to take off. But one particular point that seems very relevant to point at is some early work done by Frank Rosenblatt at Cornell back in the late 50s. And so he invented an architecture and sort of techniques that was referred to as the perceptron. And at those times, the perceptron had huge expectations in front of it. And so these days, there's a lot of angst about the level of, I guess you could say, hyperbole as to what deep learning is able to do and what it might be able to do in the near future. People think there's a lot of popular press articles, things you might see in the news that go a little bit over the top. But what Philip and I think is fascinating to point to is looking at articles like this. This is from the New York Times back in '58, talking about the work by Rosenblatt. And it's extremely hyperbolic. You can see there, look at the text, it says, there's an expectation that the perceptron, and they refer to it as a thinking machine, will be able to read and write, within the year, sort of thing. And so then obviously that never came to pass. The perceptrons had a strong limiting factor in the types of representations they were able to learn. And then, so although it started out extremely promising, there was high expectations, it really quickly came to a halt. And so things like being at these machinery being able to read and write never came to pass. Looking at the origins of deep learning is also extremely fascinating because we can see a couple of trends that exist even today. And so one of these things, as we dive into in the classes, we would examine how the perceptron works. And you can realize that there's a lot of strong correspondence in the basic mechanisms of the perceptron as Rosenblatt envisioned back in the late 50s, and the types of neural networks that are in common use today. It's a really surprising amount of similarities that one can see given the amount of time that's elapsed. Second is even in these early stages, you can see the strong reliance on hardware and hardware of an extreme capability at driving models of this kind. And so you can see that even in the very early days of deep neural networks, back in the late 50s, they were talking about building specialist computing, such as this article is referring to the Weather Bureau's $2 million supercomputer that was being used to power these types of systems. And it even refers to a specialist system that was going to be built to enable the perceptron to do this reading and writing task at a cost of $100,000. Now, even today, to many of us, certainly to me, those are big numbers. But if you project, these numbers forward in today's dollars, they're even larger than the sort of the raw values you see. And so what we did examine in the deep neural networks class is that that hardware is deeply intertwined in terms of the progress of deep learning, and as we see it emerging today. So that's sort of a backwards looking quick consideration of some of the origins of deep learning. One of the other questions that comes up is, well, why did it take so long to become so dominant and start being able to do so many of the amazing specialist tasks that we see it being able to do today? Why, if you knew some of these core principles back in the late 50s, did it take so long for us to see things such as extreme results in image classification? And a core part of this reason can be seen through the progress of hardware. This is a figure you'll see in our class of deep neural networks. On the left-hand side is looking at the rate of compute demand growth in common forms of deep neural networks that are have been invented in the last 10 or so years. And this illustration is really interesting. And again, I'm talking about the one on the left-hand side here, whereby the y-axis is the number of petaflops it takes to train individual architectures or individual systems, if you will. And the x-axis is the year that they were invented. And so what you can see is an evolution of the compute demand of state-of-the-art deep learning evolving over recent history, but through the period of time where deep learning really has been entering this renaissance period, and we've seen so many breakthroughs occurring. And what this figure illustrates to us is that deep learning requires an increasing amount of compute that probably has never been seen before in all other fields of computer science. Because what we see is that every 3 months, there is a doubling of the demand in compute. And so if we look at, if I just advance the slide, I believe AlexNet is one of these inflection points in the history of deep learning. People often refer to it as the point when the world woke up in terms of the capabilities of what deep learning was able to do. And I've highlighted that point because that's one of the most extreme, left-hand side points. You can really say that is one of the signals of the modern day renaissance of deep learning. And then moving forward, as we go to as we move through time and you look at some of these other systems, you'll start to recognize some of the labels that you've seen, or some of the system names you've seen before. So I know many of you are so interested in AI, you want to know more, and you'll recognize things such as VGG, that was a breakthrough computer vision method invented in Oxford. You'll see things like ResNets, that was a breakthrough computer vision method that allowed us for the first time to go beyond depths of 8 to 12 layers all the way down to 150. And many of you might be interested to know that was invented in Beijing in Microsoft Research Asia. And if you move forward along in time, you'll see systems such as AlphaGo, created by, of course, DeepMind just down the road in London. And what connects these types of systems is this insatiable demand for compute. And so many of you probably have heard of famous laws. We call them laws, but of course there's some more artifacts of a bunch of different technologies in relationships. But laws such as Moore's law, which has been in effect now since many decades, and increasingly chip designers are struggling to keep up with Moore's law. And what does Moore's law state? It states that, well, there are different ways of interpreting it, but one way to interpret it is that every 18 months, compute will double for the same cost point. And so what I'm saying to you is that comes straight out of computer architecture. It's been it's been active now for decades, and now we're starting to struggle to keep up with it. And then it's important to think of that, computer architecture law, and as it relates to the empirical observations we've been seeing in deep learning, which I'm telling you is seeing compute demand doubling every 3 months, so a much faster rate. And so this brings me to an important point, one of the reasons why we didn't see deep learning breakthroughs for a very long time between the period of, for example, Rosenblatt, or you can pick out some other type of breakthrough technique and method back in the 50s, 60s, and so on. One of the reasons why none of that was actually at all feasible in the intervening period was for reasons that we see on the right-hand side of this figure, which is plotting the rate of growth in compute as observed in various types of computing systems from the period of the perception. So you can see things around the 50s. You can see famous systems like the ENIAC much earlier, moving forward through things like the Cray supercomputers, all the way up to recent computation that was available in the 2010s. And what's fascinating is that none of these computing systems, none of the computing systems that existed between the 50s and up until the 2010s had the raw compute capacity to service the needs of AlexNet. If you actually combine these two y-axis and look at them closely, these supercomputers that you saw in the 2010s simply could not train an AlexNet style model. And because of that, we didn't see AlexNet style results being at all feasible. And so that is an integral part of the reason why deep learning could only become possible at the period of time when it started to emerge. In short, the compute was completely absent. And that's a fascinating observation that we will dive into in the course, and we can sort of expand upon that more greatly. But what I think is a good way to segue is into not only because there are more reasons than just compute that underpin this deep learning renaissance. And so commonly people talk about three pillars in the area of deep learning. When they think about why is deep learning now here, what's really driving it forward, not only is it the hardware argument I've just discussed, I've mentioned the extreme need for compute. I've mentioned why the compute is one very strong reason why we could not have seen this revolution up until the period when it actually started to emerge. But is only one of the three pillars that drive this whole revolution. And so commonly people will discuss compute, which you see here in the middle, as one of these three pillars, these three key reasons why deep learning is here. They also will discuss the number one issue that you see listed on the slide, and that is the availability of large-scale data. And so similarly to the effect of not having compute available up until the recent period of when deep learning took off, we also did not have data sets that were able to train large neural network architectures. And so if you have, it doesn't matter if you can invent a really nice, interesting neural architecture, and even if you have the compute available, you also need large amounts of data to be able to adequately set these parameters and have these models behave in the way that we've seen them behave, whereby they're able to provide extreme levels of accuracy, for example, in various machine learning tasks. So one of the key pillars, along with hardware, is the availability of data, which only also is relatively recently available. There's a variety of reasons for this. The advent of the internet and the ability to access all this data and aggregate it together is one aspect. There's also been a conscious effort in the machine learning community to build data sets of this kind once they realized that they needed much, much larger data sets than they typically had available. And so in this course, we would talk about a critical juncture in the evolution of machine learning, which was obviously also critical to the progress of deep learning, and that was the creation of the ImageNet dataset. Up until that point, datasets of that kind just were not in common usage. And so ImageNet produced for the community a carefully curated set of labeled images at a scale that you could start to see deep learning take off. And so those are the two key pillars that people talk about, and they're often also joined by a final one, which can be framed in a variety of ways. And essentially, it's the algorithmic and the theoretical aspects relating to deep learning. Many of these methods, I mean, as you look into it deeper and deeper, you can see many of these methods and principles were known far earlier. So small amounts of them, certain aspects were available even in the late 50s. But along the period, where there are different, ebbs and flows in the interest. And as we go into the course, we break down the history of deep learning. We mentioned, for example, that there was a period when deep learning was deeply, deeply uncool, where nobody was interested in looking at it. And we said, so we want to understand why was it the case? And it was during those periods, though, that other pioneers, people like Jan LeCun, like Hinton, like Benjo, they kept the area going by coming up with other series of techniques. So Jan LeCun really perfected the neural network of convolutional neural networks that are so effective with images. And so essentially in this third area, it's really also being powered by a mixture of rediscovery of old methods, refinement of other methods, and then some truly really interesting breakthrough methods that probably mostly have emerged once they realized that deep learning had all this potential. And so depending on what your preference is for labeling certain techniques, you can argue that perhaps transformers, things like GANs, even more nuanced techniques like batch norm have all played a part collectively in providing us with an algorithmic and theoretical underpinnings that provide us with a third pillar. And it's only with the availability of these three things, if we just had lots of compute and we had lots of data, but we had no method to use them, if we did not have neural networks, but other types of methods, they wouldn't be able to necessarily exploit the scale that deep learning is able to exploit. So all three things really were necessary, and all three things only came into being, only came into availability to the world at a certain time that is often denoted by the emergence of AlexNet, which you can see the effect of AlexNet being illustrated here on the bottom right-hand part of this slide. That this figure actually tells a very interesting story. And so what it tells you is that ImageNet was a competition, a worldwide competition for the design of machine learning models that could classify objects within images. So, recognizing a cat, recognizing a golfer, recognizing different objects. And what was found that in the start of this competition that was based using ImageNet, the large data set, initially, all of the methods were not neural network based. So you'll see the 2010 result. And by the way, the y-axis is error within this data set, so the amount of error. So it looks like it's the 2010 result is maybe 27%. So 27% of the time, the machine was getting the wrong answer. And moving forward, you can see the results moving down and lowering. And so what's interesting, though, is you might see that the rate of progress had a leap forward between 2011 and 2012. And so something happened in that intervening period. And what that thing was the adoption of deep learning. In 2012, the winner of this competition was the AlexNet architecture. It used a convolutional network. And it really was a signal to the world that deep learning methods could provide, really strong results. And it turned out beyond just the area of computer vision, but it's, bled through into so many other different types of machine learning tasks over time. And so what's interesting is from that 2012 result forward, where we had this big jump forward in terms of accuracy, all those methods were, from that point forward, neural network based. And so, and to kind of bring this full circle, a result that we saw in 2012 would not have been possible without these three pillars being in action. Let me just go through a little bit about each of these pillars, just to give you sort of some raw information about each of them. Pillar one, this availability of large data. Where does the data come from? Well, places like Facebook. You can see millions and millions of images being uploaded into these systems of this kind. And so suddenly we have this rush of data being available. Companies like Walmart, they now routinely process petabytes of customer data hourly. A system like YouTube, where you're actually watching this video, some of you perhaps, is constantly having videos being uploaded to it at a almost difficult to get your head around sort of amount of data, right? 300 hours of video per minute. And probably these data points are somewhat dated. Um, I'm sure if we looked for the very, very latest results in all these facets, these numbers have even inflated further. And this is just a snapshot of the types of scale of data. It's kind of putting some particular numbers to the argument that I said that before data was needed, and I said that before data was starting to become available. Well, these are the types of sources where you can get this data from. So that's pillar one. Let's examine pillar two, this available of cost-effective compute. The story here really is that in 2012, a variety of people, but in particular, the folks behind AlexNet, people like Hinton and others, they realized that GPUs were a perfect type of computer architecture to perform the compute that neural networks require. And so there was this strong correspondence between a certain type of processor that was already available. It was already a commodity. You could buy GPUs, these graphical processing units, just completely off the shelf in any tech store. And they were being used for graphical tasks, things like rendering, playing games, and so forth. And what they realized with this style of chip that is that excels at doing things in parallel, that can be made to do things like matrix multiplication, which are the building blocks of neural networks. Is something that this is a detail we'll get through in the class, but just to keep in your mind, this is a commonly repeated computation that's a raw building block of neural networks. Turns out that GPUs can do this at an extremely efficient rate in terms of price, in terms of energy, in terms of just raw speed. They are fantastic workhorses for neural networks. And so once we realized that they were already available, that made it very easy for people to start doing these types of relatively large, particularly at that time, neural networks. So cost-effective compute was discovered through happy coincidence, I suppose. And that became pillar two. And then this is a reinforcing, each of these pillars are reinforcing. So once you realize that you need data and data is available, then you can start to justify the collection of more data. And similarly with the case of hardware, once you realize that these methods are going to be so effective and that there are existing pieces of hardware you can use to bootstrap the process and demonstrate their effectiveness, then there's a self-fulfilling cycle that people want more of these networks to do different tasks, to do larger tasks. They want to push them even further. And so then suddenly there's money and time and resources available to create hardware that's even more specialized. So part of the story is that really from 2012 forward, people started to even further specialize the hardware that's underpinning neural networks. And that was because neural networks, one of the reasons for this was neural network workloads are extremely well suited to what is something known as hardware specialization. For example, the way that you can train a neural network, it makes it very easy to parallelize the compute within a chip. And so if there was a lot more dependencies in a neural network, if they're architected differently, if training was not done in the way that it is, that might not be the case, but it just so happens that it is. And so therefore, the properties necessary in the algorithm are there to be able to do it very fast as you start to make more and more and more specialized pieces of hardware. And my final point on this would be that none of this hardware would necessarily be the final, would be enough without the availability of software frameworks, things like PyTorch and TensorFlow, and even forerunners like Torch, like other software that we don't even use anymore, that really bridge between the hardware and the deep learning researcher, enabling them to get the most out of the hardware and enabling them to do so relatively easily with these days, or even wasn't that long ago, these, especially these days with just a few lines of Python, you can really have high utilization in your hardware, training very large networks with what is relatively low amounts of of hardware costs given for what they're trying to do. If we just look on the right-hand side here, this is explaining the story. This is probably a clearer illustration of the story I discussed last 2 slides ago, whereby in the ImageNet challenge, you could see the line is showing you the decrease in the error. And then we can see this really steep gradient between 2011 and 2012, and that's completely deep learning powered. Prior to that, they had really flat. If we extend back before 2010 to research coming before that period, they had pretty plateaued performance on complex tasks with non-deep learning methods. But you can see from 2011 forward, we see rapidly falling error rates. And then the bar chart is actually a count of the number of submissions to this particular competition that uses deep learning. So you can see in 2012, AlexNet was not the only one. There are others. But then as soon as people realized the potential of these techniques, you can see in 2013, 2014, the number of submissions to this competition that were based on deep learning just went through the roof. And then this is one picture that's very clear in the area of computer vision, but this same story has been replicated in many other domains. Most recently, NLP is probably the last most recent domain that's really been revolutionized. Potentially, I guess you could also say graph processing too. Let's talk about pillar 3. What I mentioned before, it was really a potpourri of algorithmic and theoretical techniques that we've been able to lean on that were just, obviously essential to move things forward. But within this, I think the most clearest discussion we can have is about this, real transition from non-deep learning methods that were heavily reliant on features to deep learning methods that do what is called representation learning. And so they do not have explicit features that are then fed into a model or a classifier. What they do is they learn representations that transform the raw data or some sort of basic representation of that data. And they learn a series of transformations that are akin to features in some sense, that are tuned for that task. And the key thing here is that they're learning it algorithmically. There's no human in the loop here. So they learn. So in a deep learning setting, if you're doing a computer vision task, the transformations are learned purely from the data. There's no human in the loop explaining semantics about if you want to recognize a building that has this sort of shape, there's no one saying, these sorts of colors are often corresponding to these sort of classes. It's completely data driven, which makes it incredibly scalable, and is a big departure from what was done previously. So previously, there's these sort of comments at the top end here where we talk about handcrafted features. That's talking about how prior to deep learning, the de facto standard approach, say in the computer vision area, was to use handcrafted features that people would agonize over, write whole PhD thesis about, trying to come up with transformations that would be discriminative across different classes of computer vision tasks. So it's SIFT and SIRFT, for example, very famous ones in the vision domain. MFCC is a famous one from the audio domain. The pointers, they were engineered by hand. They incorporated subject-specific knowledge. So you can start to see why this is not a very scalable approach. If it's built by hand, it's tied to the same task. It's tied to a particular task. Then when I need to try a new task out, I have to start from scratch again. I have to start thinking to myself, what sort of features might be useful here? What sort of transformations? What are the property of those transformations? What do I have to be invariant to? And so on. And then the way that people design models then were to have very complex features that fed into relatively simple classifiers. And so at that time, dominant methods were things like SVMs, or even KNNs, so nearest neighbors, very simple classifiers if you had powerful features were being used. And that paradigm completely shifted under the case of deep learning here, where we have transformations being learned from data. So this is a key part of this third pillar, probably the most concrete part that one should talk about. And so now we've talked about, and we've talked about the overview and in some depth, each of these three pillars that really drive deep learning forward and allow it to go. I've gone way over time, but let me just tell you a little bit about where I think the road forward may lie. Obviously, there's a lot one can say here, so I just picked out three things that might be interesting to you from the sort of the setting of where deep learning is a mainstay of machine learning today. So where is it going to go in the future? One thing that is increasingly coming about is the fact that there's not a lot of radical changes in a lot of the methods. There's a lot of introducing a new architecture, a new method of training, and so on. But a lot of the core principles are staying constant, and a lot of the gains are coming simply from scale. So they're looking at ways, how do I apply a faster processor? How do I learn from more data? Can I learn from unlabeled data? Can I let myself combine unlabeled and labeled data? Can I expand, therefore, the amount of data I can learn from? Can I have a new sort of tweak, relatively small perhaps, but can I conceptually change a method a little bit and then see a big gain from it? So a lot of what's happening, at least right now, are steps forward. Some of them actually that look fairly large in magnitude, but are conceptual steps that are relatively small. So that's one place that we currently are when I look forward to what we're doing right now. We can see some exciting architectures and methods emerging. So I'm sure many of you have heard of transformers. In the deep neural networks class, we'll dive in to explain the difference between a transformer and other types of architectures. There's other types of methods of training and tasks. So some of you might have even seen these generative and synthesizing types of models, such as stable diffusion, where you can even combine modalities to synthesize new images from textual descriptions and so on. And so I think those sort of tasks and those sort of architectures are going to start to really proliferate. But an interesting question, of which we don't have totally satisfactory answers to right now, where will the next truly big breakthroughs come from that will push the area forward? People want to do things such as bake in common sense into architectures. They want to combine different modalities. So maybe some of the breakthroughs might come from those areas. But what is probably fascinating right now is just how far things are being driven by relatively, you could say, incremental sort of improvements to what is already known principles. But anyway, we can debate this further in the class, and we do. One thing I want to highlight is that there's a fascinating term that was coined by Sarah Hooker in the last couple of years. She developed this phrase called the hardware lotteries. And so there exists, if we extend this, the idea of hardware lotteries is that through the success of an algorithm in terms of whether it fails or succeeds within the area of machine learning can be strongly influenced by how much assistance it gets from existing pieces of hardware and, by extension, software. And so what this means is that in the area of deep learning, as we get more and more specialized hardware, certain types of algorithms are being more strongly promoted because they run faster, they can consume more data. And even though if there might be a similar architecture or even a completely different way of learning, that it, conceptually, and then depending how you measure it, may theoretically have similar or even lower amounts of compute needs than the existing methods. But because of the specialization in the hardware, these existing ideas can actually still be more efficient. And then if you want to sort of deviate from these existing ideas, you start to pay an increasing penalty in efficiency that is not born from the core understanding of the idea, the core fundamental idea itself, but born out because of the specialization that's occurred before it. And so you could think of the evolution of these sort of algorithmic methods being heavily subjected and conditioned by the existing hardware and software, which may just be a lottery in and of itself. So that is, in a nutshell, some of our, some of the thoughts that come to mind when we talk about this renaissance of deep learning, where it came from, why it's so popular, and some of the basic questions that often get asked, such as why did it take so long, or what's the relationship with it and with hardware and data and so forth. Um, I just want to conclude by saying, um, if you enjoyed this discussion that we've had today, you'll really like the course Deep Neural Networks taught by Philip and myself. We go through this information in far greater depth, and you can talk to the TAs and really get a much deeper appreciation of this area. But this is really just food for thought and sort of priming discussion that we could have in our course. Um, I should say that the Cambridge AI Academy that I mentioned at the start currently is running 2 courses in this calendar year that are happening monthly. There's this deep neural networks course I've mentioned a number of times. We also have a different course called Machine Learning Systems that examines this interaction between systems and hardware design and state-of-the-art machine learning techniques. Um, if you've enjoyed this information series, then you should feel very welcome to come to future editions. So we've locked down 2 dates, September 23rd and October 7th, to hold similar information series where we'll talk about different topics. The next one is going to be about the deep learning life cycle, and the one after that will be diving into largely the software stack that underpins these methods. So these are completely free. We're going to make them probably a little bit more interactive. Please send us feedback, and we'll take that feedback into account to make them more fun and engaging. And then, and again, about the AI Academy, if you're interested in some of these courses, you can sign up. I've got the URL there. We have additional courses that are going to be offered in 2023, offered by the faculty that I mentioned at the start of this talk. And then for those who are really interested in this material, you should seriously think about joining what we're calling the Cambridge AI Student Academy. And it's free. There is a Slack system you can join to meet other students and to talk to faculty and staff of the academy. There is a mailing list. You'll be invited to events of this kind and other ones also. And it's just a way for you to really explore the AI space completely free, regardless of if you want to take a course or not. So that is all I had time for. I want to say I hope to see many of you next time. I'm so delighted so many of you turned up today. And and again, please give us some feedback. And otherwise, we will see you next time. Thank you very much for attending. Take care. Bye-bye.